minutes less today. So I'll be discussing that. I got about three different requests or explanation. One, I'm not taking names of students, but yeah, those are something like this. The first student asked me two questions. One is that why 1H and 3H, if we just compare this proton and tritium, we'll see that the gamma of 1H is less, actually slightly less than gamma of tritium. And he asked me why this happens, because we know in tritium actually we have one proton and two neutron, correct? And then if I look at the proton has gyrometric ratio is about, I don't know, about most likely about 5.5 plus, whereas neutron has something like minus 3.8. So we expect that if I have two neutrons coming along with the proton, it should ideally go down with this negative thing is coming, rather than the gamma going up, correct? But again, as I told, this neither the gamma nor the total spin of the nucleus is any way kind of a direct sum of any of the constituents. It is not. How this particular, because what happens is that when these protons and neutrons come together inside this nucleus, other forces other than the normal electrostatic forces, other forces like strong force, weak force, they start coming into play. And the physics of nucleus inside, right, the nucleons inside is quite different. We are not even touching that. We are not even discussing this. So what happens is that instead of going to the rigorous way of understanding that how these constituents particles actually give rise to certain feature of the nucleus, people have tried using models like different nuclear models. They have kind of given some sort of, those models are not actually rigorous, mathematically rigorous models, but kind of working models that can explain to some extent. So one is this I was talking about at the very beginning of the first class, maybe, that it is the shell model that tries to explain that how come it is not exactly an algebraic sum of all these constituents that we see as the effect of this nucleus, correct? So that is basically as if that we have kind of the shells. If a particular shell is being completed, then their effects is kind of nullified. That is why if we have, for example, tritium is having the tritium, this also have spin half, and one is this also spin half, whereas the 2H has spin 1. Correct. So it is really not going into that, okay, we are half, then another half is coming, that's maybe 1, then another half is coming. So we expect this will be 3 by 2. 3H should be 3 by 2. Like 1 half, then 1, then 3 by 2. But no, it came back to half. So as I told you, these are difficult to predict just from this thing. Okay, second question, the same student asked, is that he was not sure about that what do you mean by this coherence the concept of coherence, or how come the RF, the radio frequency is creating that. Now the question is that if you really want a theoretical perspective of it, then I can only suggest you to read something. You can read something, then you can come back to it. Is that you read this particular chapter. It's called Rabi oscillation. What happens is that in the Rabi oscillation, he has II Rabi. He is a Nobel laureate. He discovered that if I have the normal Hamiltonian, which is basically the H naught, we call it H naught, that is proportional to this B naught, the main Hamiltonian. I'm not going to much into the detail. Then the RF pulse, which also often we call as a H1, is a small perturbation to this big Hamiltonian. That means you are basically having a spin system, they're in equilibrium, nice, and then a little bit of perturbation I'm doing this particular RF. And this perturbation, after you actually do perturbation theory and it's much deep into the math, then it can be shown that this coherence, which is basically again represented by the off-diagonal element of density matrix. So as I told, your question, a very innocent question, but its answer is not that innocent. The answer is really gigantic. So I cannot really go into this particular thing. But one thing I can tell you pictorially a little bit, that what happens is that we had seen before that this particular scenario, I have drawn this scenario many times. So we have this particular thing, and then we have all these ones, and they do not have any phase coherence to start with. They are all over the place. And then if we have this RF pulse, what are the RF pulse I was talking about? So RF pulse is basically a coil like this, correct, in particular. And suppose this particular RF pulse that is a linear field that is oscillating back and forth. All these pulses that we apply, they are basically a linear oscillation. So if our oscillating field is in the x, so suppose this is an x direction, this is an x direction. If I have the oscillation along x direction, then mathematically, through this whole thing, mathematically can be shown that in the orthogonal direction, that means if I have the oscillating field x direction, this linearly oscillating field x direction, then in the y direction, they will start having bunching. They will have the phase correlation will start coming in. This is not going to be the case like this. This is, you can think in this way, that like for example, when you have a swing, and then the swing is going on, and then you started giving a push at a particular period, right? The resonance phenomena will come in, and then it will start oscillating with the same frequency as you are pushing, correct? So this is the oscillation. So this is very similar to this, but some kind of resonance at resonance, this particular thing happens, that a maximum bunching happens in the phase keep. But again, I must always tell this, that this particular picture that I have tried drawing, this is a classical vector picture for a quantum mechanical thing that is happening inside. This coherence, which is basically a coherence between the alpha and beta states, is absolutely quantum mechanical concept. Alpha, beta. So what happens is that when you give a pulse, mathematically, all those which are in alpha state, in the top state, they go to a particular state called a superposition of alpha and beta, and that's given by this. That is the mathematics going on inside. Whereas those which are in beta state, they go to a state represented by alpha minus beta by √2. This is the mathematics that's going on. Now, once this particular these states are there, where these states are there, it can be shown that the corresponding density matrix, has an off-diagonal element. So you get a 2 by 2 matrix, and it's going to be an off-diagonal element like this one is present. These are non-zero. Earlier, when they were in this particular state, alpha and beta, these are not there. And then mathematically it can be shown. Actually, I take an NMR theory course, a full-fledged 1 semester course, where rigorously I explain these things and I prove these things, but it's very time consuming. Then it can be shown that these ones actually can be represented as something like a bunching of phases, and that is how this particular thing is happening. So anyway, so I understand that it was not too clear, and it is not your fault, but partially it is my fault that I have not made it clear, because the amount of time it's necessary to make it clear is too long. But nonetheless, if you want to connect to me, and if you are present today, you are connect to me, then you can do it. Certainly. Okay, I need to plug in my laptop with a charger. Okay, sorry about that. Okay, now this is fine. Well, kind of a half quote answer I gave. Nothing can be done. The second question, the second mail that I have got regarding is that somebody asked me that I have spoken about kind of some days when I was talking about the multidimensional MR. He was asking that I talked about 2D and 3D and 4D. So all this 2 and 3 and 4, where from they're coming, right? So I can give some answer to that. So the idea is that suppose you have I can draw a particular thing. So basically N and H, and you have C, H, R, then C. So this is basically one residue. Those who are an expert in protein, they can tell it. I'm not an expert in, also not this one. So, okay, so this is one residue, and this gets repeated, correct? So now I have this particular H, this is called the amide H, and then this nitrogen, then carbon, the C alpha carbon, and then we have this alpha H, and then you can have different R for different residues, and then we have this particular thing. Now the question is that what do you mean by different D? So the different D is in each D you have a different frequency being encoded. So it can be that you first create, you first pulse the proton. So you first take a pulse on this particular proton, and this particular proton, and then this particular proton plus. So this particular proton has a frequency. Suppose this is basically some omega H or N I can take, right? So therefore, when this having then this, the coherence will actually be going something like omega H N some T, right? And then you transfer this particular one to N, and then it goes to this, and then those N, and then you, after transferring, then you leave another time. So first you put up a pulse. First you put up a pulse on the H, this H, and then you leave for some time. I call that suppose T1. Then you transfer. This is basically transfer process to N, and then you, after this, you leave another time 2. So therefore what will happen is that now there is going to be some cosine omega H N T1 is already there. Then it is going to be on top of that cosine omega N T2, correct? And then you can also, in the 3D, after N, you do not stop there. You take it to the C, or this, either this way or this way. So then after you take it to the C, then you actually, after transferring this to the C, now you go again and a T3. And this is basically that you have this coherence. Coherence means you have this alpha, beta, the magnetization, the bulk magnetization you create. And after creating, you flip this. So this flipping is done by one pulse. Now your experiment starts. Then you give some time. So this is having a Larmor precision. This Larmor precision is about the one that you have just created, this particular magnetization, correct? And then once this is done a little time, and then you transfer it to something else. This transfer is done through J coupling. I have explained that as well in one of the lectures. Once that has been transferred, then you wait again for another T2, and then these are the times that you are waiting. And then once this particular all three are done, then what will happen is that you get a signal which is a function of T1, T2, and T3. And then how will you doing it? You basically take the value of 0 here first, and no gap, 0 first, and then you start from 0. So this is the first data point. All 3 times are 0. No chemical state evolution is going on. Just transferring and transferring and transferring. That's it. Then you take, this is 0, this is 0, so some delta, some amount of increment. Then you take 0 and then 0 and 2 time delta, and then it goes on till this is the n time delta that you, the last one you want to take. Then you come back, you make it 0, and this you make it, this is some delta which is a little different, delta prime, and again it will start from 0. So then 0 delta, and then u prime, then 2 delta, and then 0. Oh no, this is basically, this is delta, and then it is delta, then 0 delta, and then 2 delta. So that means you are, look how, and each one of them you are basically having a separate experiment. That is why in a 3D experiment is such long. So you will be taking one experiment with all 3 0, all the 3 gaps 0. Then this is incremented a little bit, then this is incremented a little bit, and you complete this. Then you increment this one step. Then you complete again the entire up to the entire thing you complete. Then you go to the next step, that means 2 delta. Then you complete it. So basically it is like a loop. So for each value of this, and then after this whole thing is done of this one, then you increment this one time. So therefore you can think that how long it will take. And then once you do this, this particular thing will basically give you a spectrum which will have a box like this. Where this frequency is your omega h frequency, this frequency is your omega n frequency, and this frequency is omega your c frequency. This and this. And I was talking about this h, this n, and this c, for example. There are many other. You can have this h, this n, and this c, or you can actually go and further up in c alpha, c beta. So there are many experiments. But this one. So therefore, a particular peak here will have basically three different particular peak will have three different coordinates, correct? So the coordinate, this is one coordinate, another coordinate, and this coordinate, and this particular peak will be actually telling you that I have a residue which has this particular NH chemical shift, this particular N chemical shift, and this particular C chemical shift. That means that this by coming from a particular residue. The next residue, maybe these particular chemical shifts are different, so you'll get another peak like this, which is a different omega h, different omega n, and this is how this particular thing. Now therefore, obviously, now if it so happens that suppose two of them have exactly the same omega h and omega n, exactly the same, these two are exactly same, that means this point is here, but they might be having a slightly different omega c. So then what will happen is that those two peaks will be basically having, one is here, another is just on the top, because they have the same omega h and omega n. So then in this particular plane, they will be having exactly the same. So this particular plane, this is this particular plane, which is the plane, this particular plane, they are having exactly the same plane, same position, but in this dimension, they have two different point, because this omega c is different. That is how you can actually separate them in the third dimension. This is basically 3D, three different dimensions, three different chemical shifts. Now you can have four different chemical shifts if you want. A, like for example, H, then N, then the CH, the C alpha, then the CH. These four, 1, 2, 3, 4. This can be 3. It can be 5. 1, 2, 3, 4, 5. So basically, how many you are basically doing? So you start from there, transfer, evolve, transfer, evolve, transfer, evolve, and you just keep doing it till it's there. So this is how 3D or 4D thing is all about. Okay, I have the second question done. The third question is that it is about the last lecture, the relaxation lecture. It says that I was talking about many times that it is exponential. I'll tell you why it is exponential, but I have not told it. Correct, I have not told it, and that is related to this particular plot that I was making, like exponential, like I am doing exponential, correct? Why this exponential? Why this recovery of the why this recovery is not say for example, why this recovery is not something like a straight line like this? It could have been a straight line like this, correct? As it is recovering the minus z, flipped minus z to plus z, this recovery, why this exponential? Now this, why this exponential? That is kind of why this exponential, nobody knows. It is exponential. It is basically it is done this way. Bloch, the Felix Bloch, the Nobel laureate, he measured these things, and then he found that this is basically this particular way it is doing. So he proposed that, well, we understand a situation that mathematically I can tell you that this mz as a function of t, mz is the z component as it is doing as a function of t. This particular one is given by some r1 rate constant, and then this is mz at, oh sorry, this is m naught, the minus mz t. So what he told us, m naught is basically the equilibrium value, correct? And then you are at any point of time, how far this particular value at any point of time, how far this particular value away from this equilibrium value, this particular quantity, and this is a proportionality constant. So that means the rate of mz is proportional to the deviation of this mz from m naught. This is the Bloch equation. The Felix Bloch told this. So this is the equation, and then if you solve this, then if the solving this, then it comes something like this. So mz at t as a function of t is going to be m naught 1 minus not tell the whole thing, that is m naught minus m naught minus mz 0 e to the power t by t1, or I have not done t1, so minus r1 t. So this is the one. So that means it is that at any point of time t, this m naught is the equilibrium value, correct? The total. So it is basically the equilibrium amount of magnetization, whatever it is. This is my m naught. So if I just flip it, correct? If I just flip this whole thing, it becomes minus m naught. That means this particular thing, mz at 0, is minus m naught. So what happens is that if you have a minus m naught, the m naught minus m naught, so 2m naught. So if I just flip this equation actually takes an equation is something like mz t is equal to m naught minus 2m naught r1 t, which can be also written that in this, if you take mz divided by m naught is 1 minus 2 times e to the power minus r1 t. So therefore, you find that if you just plot this one, the mz with respect to normalized to the equilibrium, then it is starting at t equals 0. Correct? Just t equals 0. What happens is that is 1 minus 2 is minus 1, obviously, which is basically minus 1 I was talking about. And then at t equals infinity, when the t equals infinity, what happens is that at t equals infinity, this whole thing is 0. Correct? It's minus r1 t. T is infinity, but a long time, after a long time, this whole thing is 0, so it will become 1. So it starts from minus 1 because 1 minus 2, and then it goes to 1 in this particular fashion. Now this particular thing that it is exponential, this was observed. It was observed by Felix Bloch, this particular thing. Later on, other theories came later on, like for example, Redfield. There is another A.G. Redfield. He was is a big shot in NMR. He gave his Redfield theory, and then later on we understood even further where from these things are coming. But anyway, that is a deep core in relaxation theory. I don't think you asked for that. So yeah, so the source of this exponential thing is it is inbuilt, it is there, it has been observed. And then Bloch, he gave a very simple Bloch equation. It is not going to deep into the relaxation thing, how this particular thing is changing, and then that particular thing is there. Anyway, so this is basically the three things that we asked for. And then as a new thing which we thought of doing is basically I promised that a little bit I'll be talking about say what is called anisotropy, the space anisotropy. So I'll be talking a little bit. I have about 10 minutes more or less. So the anisotropy is something that we'll be talking more into when you'll go into the course. So you have a full course ahead of you. This is just the 5 lectures in the beginning, so don't worry about it. It will be covered again in much detail later as well. One particular thing is that I'll just tell you. One thing is the ring current I was talking about, right? This is the starting of anisotropy that we can think about. So if you have, say, a propane, if you just have propane, then the chemical shift, you'll see that this particular proton is a chemical. Now again, the chemical shift I will talking about in ppm, and I have not discussed what the ppm scale is all about. What's the definition of ppm scale, because I know that ppm scale will be discussed. I have seen the syllabus. It will be discussed in some scale, assuming it's some scale. And it's important to know this particular thing, that in the ppm scale we start it from 0 here. There is a there's a reason behind this as well, this particular thing, and then it goes increasing in this direction. So this is your ppm scale, and the lower the number, that means if you're going this way, if you have 2 peaks, like you have 1 peak over here and you have 1 peak here, correct, the peak which is having lower number, correct, is more shielding, and this one is less shielding. Shielding means the I was talking about, the chemical shift is giving that you have the nucleus, and then you have this electron cloud which is shielding it, correct? That is, I explained it with this current and all those things in few of the classes. So this particular thing, that means the more the number is, the ppm value, the larger it is, less shielded. That means electrons, the effect of electrons surrounding it is less. And more I'm going in towards this direction, that means you are having a larger. In fact, it can be go to negative number as well. It can have -1 ppm or -2 ppm is also. That means it is even more shielded, something of this kind. So now I'll be coming to this particular thing. So I have 0.9 ppm, and then if this, you take this particular proton, they come at 1.3 ppm. Okay, fine. Now if I have an ethyl bromide, you take the same CH3 and then you get a CH2, and then you take a Br, you replace this by a bromine, then this one comes at 1.7 ppm, and this particular proton comes at 3.5 ppm. Now, why this particular thing happened? So let's see. So 0.9, it went 0.9 to 1.7. So it has reached into a larger direction. That means less shielding. Obviously, it is less shielding because we have an electronegative Br, correct? So this is pulling this electron. So therefore, this electron cloud is not surrounding this particular proton, but this electron cloud has been pulled through this particular towards the bromine because it's electronegative, and hence this particular proton is more exposed, less shielding effect, and that is reflected by increasing this number, even for this one as well. So this is not coming from any anisotropy. This is basically a simply inductive effect, and you'll be going through these things in much more detail with a lot of examples later on. But let me tell you another molecule, N-butene, and then this is say something like this, and then CH2, and then CH, and then double bond CH2, and then this one comes at 4.7. Okay, now here you see a lot of downfield shift. Like for example, we had this was having 3.5, correct? This was 3.5 because it is very close to this bromine, so a lot of pull was happening. Obviously, the effect of pulling for bromine was less here and more on this particular proton. So therefore, I can understand. But here, that is no such electronegative thing is there. Then why this particular 4.7? Why? Who has taken out all this electronic cloud around them? So this is basically a question that might be asked, that we do not have any Br or any chlorine or anything, and then why this particular thing happening? So this particular happening because of this particular double bond that we have between C and C. So what is that? I have just downloaded a picture. I'll be taking this particular picture here. So this double bond, you know that if you have a CC double bond, one bonds is basically a sigma bond, right? Is head on or between the two p orbitals. But the other bond is basically a pi bond, correct? So you have this 2p orbitals we have. Now we can see that this particular thing is happening, that these p electrons, they can actually roam around here nicely, correct? So therefore it can actually make a ring. So this ring current is coming because here these p, they are free to move, correct? And as they're free to move, so you have kind of electron cloud is there which is above the plane, and they are free to move, correct? So what they will do is that the moment they will start some amount of freedom to move. And I have already told you that what happens if I have a magnetic field, right? And then this electron start to move, the entire theory, you might go maybe 2 or 3 lectures back, and then I told you the Lorentz force will start kicking in, and the Lorentz force will be such that it is going to be a diamagnetic effect, meaning that the current will be such that the effect of that particular current is going to be opposing the field that was created originally. So imagine that you have a magnetic field in this particular direction, right? You have the magnetic field in this particular direction, and these ones will be creating some kind of a ring on top and a ring on the bottom, correct? It's kind of like they will start moving, and the moment they will start moving, they will create a electric current, like an electric loop, which I have again explained. I'm not going to go detail because I've already done it. And the effect of this particular ring will be at the center of this particular ring. at the center of this particular ring, there will be a current that is being that a magnetic field will be created because of this current, which will oppose this particular magnetic fields, correct? So the lines of force are going to be something like this. So it is going to be opposing. So these lines of force are all going inside because of it has to oppose. So therefore the original one was this direction, right? Up direction. So this one has to be down direction. It has to oppose because this is a diamagnetic current, correct? And this current is necessary because of this loop was formed. If this loop is not formed, the pi electron, the delocalized pi electron loop is not formed, then they cannot make this current loop. And if they cannot make this current loop, this whole effect will not be there, correct? So this is an extra amount of loop that is being created, and that is giving this particular. Now imagine these protons which are not exactly in the middle. So basically these protons are these two protons, they're outside this. So although we have this particular field in the middle is opposing it, but because of this lines of forces are going around here, so this lines of force having a direction in this way which is matching this direction. So as if this particular portion is this effect here, if this H is in the middle, then they'll have a negative effect. That means it is going to be shielded. That means it is the B0 effect is less. So this is shielding effect will be there, and it will shift towards right. But if it is ice is outside, it is as if this ring current is helping it. In top of B0, it is added to some extent, and that means it will go into the left side. So this is basically almost like a more deshielded region it is going to be. It is not actually deshielding, but this is the ring current that is being there. So that means this one which is outside this ring current, this is adding to the original one, and that means it will be going further downfield, and that is the 4.7. I'll give you another example, then you'll understand that what happened, this particular thing is happening. So the another picture I'll show, and that picture is this picture, this Ram's picture. This is benzene, correct? This benzene, and this is again what happens is that we have a nice a ring over here. We can have a ring, and we can have another ring over here, right? We can have another, and these rings will be creating a field again, such that if I have a B0, which is in this direction, correct, then the ring will be such that the B0 which is coming in is going to be in this direction. So therefore the effect is going to be like this. And it's going to be all going down here, and therefore coming up here, going down, and it is coming up here. It's going down here, and then it's coming up outside. So therefore these protons which are sticking out of this particular ring, right, these protons are exposed to outside. This is not in the ring. They are going to see no diamagnetic effect. They not show the diamagnetic effect, but rather they'll show kind of a paramagnetic effect, is that the field is adding to this original one, and that will create more deshielded. So therefore we have the same effect, but we see that this is the C issue, this is about 4 to 5 ppm, whereas this aromatic proton, they go all the way to 6 to 7 ppm, sometimes 8 ppm, depending upon the other substitution. So why this is going further downfield? Because here I have the pi electron current even more, and that is why this particular thing is having the ring current is even more stronger. So therefore it has creating very down. But the last example that I'll be talking about, it is the opposite sense, and that is this one. I have not got a very high resolution one, so I have to work with this one. So basically in acetylene, what happens is the situation is something like this. So we have you have a triple bond. So so here what happens is that I have this sigma bond inside, but then I have the px and py, the two of these pi bonds are there, like this thing, and that actually creates a lot of like a cylindrical, almost like a cylindrical electron density inside, correct? And there what happens is that the ring that can actually form is of the thing like this. So this is the ring is being formed. So this is the ring is doing. So therefore, if I have this is the ring, then the field is going to be something like, okay, let me draw another one. So I have this H over here, and then I have this C, then I have this triple bond C, and then I have another H, correct? So therefore, you have this, the whole ring here. So we have this whole ring, or this is basically a dumbbell of electron cloud, and therefore, as this is the one, so the rings are forming. Oh, sorry. The rings are forming like this, right? So this is the ring, and then therefore the field that is being created is of the order of this. Even it will oppose. So it will oppose from this direction, but then it is going to be the same thing. It is going to be, but here it is going down. It has to oppose, correct? This has to oppose. And therefore, I now find this H is no more in this region where it is basically going up. Earlier, it was happening for the other one. So it was going into the deshielded region, correct? It was going left side to higher ppm, because this H were here in this side region, correct? We had this is sticking out in this region, not in the central region where it is negative. But here in this acetylene, what the way this particular thing is created, this H is exactly in middle of this thing where it is opposite. So therefore, this will be now seeing a situation that it is actually a huge diamagnetic effect, and diamagnetic effect is actually like a shielding. More diamagnetic shielding you have, your peak is going to be shifted towards towards the lower ppm values. Why this particular thing, that why this lower ppm is equal to shielding and higher ppm is equal to deshielding? What do you mean by ppm? What do you mean by 1 ppm is equal to how many hertz? All these things hopefully will be covered in your natural thing. But the thing is that this is something that is this H. Now this H is going to be close to 1 ppm there in up field shift, and not at 6 or 7 ppm, although you have a ring current. So this is basically the anisotropy. Other anisotropy thing, which is I don't know whether you'll be interested in, not later on, maybe, like for example, and the CSA, the chemical shift anisotropy. So this particular electron cloud. This electron cloud is not always a spherical symmetric one. This electron cloud can be asymmetric as well. So therefore, the effect of this shielding is really not same when the molecule is tumbling, because this molecule is inside this liquid is tumbling. And with respect to the main magnetic field, how this molecular this particular cloud is orienting with respect to the main B0, this effect can be different. If it is a spherical symmetric, like a spherical charge cloud, then doesn't matter how this particular thing, it is always the same thing. It doesn't matter, but it is not always true. So therefore, this chemical shift effect, correct? It is actually not an scalar effect. It is actually a tensor effect. But well, it is again. I think it is not in the scope of this particular thing that will go into the chemical shift tensor. Then we split into the isotropic part, non-isotropic part. I'm not really sure that we have designed this course to go that deep into the theory. This course is more onto an application based. You probably do not even need. In fact, that is the reason this whole background on mathematics had been kept not mandatory. It is not going to be a part of your exam as well, because this is just for understanding. So anyway, this is the thing. So there, what happens is that, just one last comment, is that this chemical shift that I was talking about, that's actually a tensor. That means it has some dependence on orientation of the molecule with respect to the magnetic field that is being created. And that tensor can be actually partly it can be going to the two part. One is called the iso, that is isotopic part. That part is not changing with respect to the movement of this molecule. This is fixed. And then there is another one which is called aniso. That particular part of the tensor is anisotropic part. That part changes. So this one, this isotropic part, that gives me the chemical shift that I was talking about, the position of this peak where it is. This isotropic part is giving the thing. However, this particular thing, anisotropic part, which is changing the effect with changing with the molecular orientation, and the molecule is orienting reorienting very fast. The tau c is very small, correct? This leads to relaxation. So I was talking about relaxation, correct? So I was talking about relaxation, that when the Boltzmann distribution had to be readjusted, correct? From the non-equilibrium state to the equilibrium one, something should be there to take this energy out of the system, so that it can release that extra energy that we have pumped in using RF, so that it can go back to the Boltzmann equilibrium. This particular part, this anisotropic part, the anisotropic side, that means the asymmetric electron cloud around the nucleus, they help in doing this relaxation. Not only this one, this anisotropy, this is called CSA, chemical shift anisotropy. This is one part of the relaxation. This is one method, one mechanism of relaxation. Other mechanisms of relaxations are also there, like dipole, quadrupole relaxation, this or that. In fact, there are theories which says that there are two different mechanisms interact. Like, for example, CSA and DD, they interact. This is called cross correlation, CSA DD cross correlation. That has even more impact onto like experiments like TROSY, that has this thing. So basically, this theory, this NMR thing is vast. Depending upon how much you want to dip down, you can keep digging. But I think at the last thing on this, my part, I would say that we have covered maybe the most of the part that is probably be required for understanding the rest of this particular thing. Yes, we have not touched the solid state, but Professor Ghosh will do it in detail. We have not touched MRI because those are different things. But as far as the liquid state NMR is concerned, which I work on, I think we have touched upon the most of the things that you need to go ahead. But even then, as I spoke in the beginning of this course, that anytime later on you encounter a particular concept that you are not happy about, not happy, I mean, you are not fully satisfied and need a little bit of mathematics.
प्रोफेसर घोष, उधर का इंटरनेट कनेक्टिविटी चला गया क्या? चेक सिग्मा को एनाइसोटोप বলেছে, सिग्मा को एनाइसोटोप বলেন, हम दोनों डिस्कस करेंगे, उनको पूछिए सर। प्रोफेसर घोष, yes,
Just a minute.
yeah. There was some interruptions maybe.
No, it's fine now.
It's fine now. Yes.
Yeah. So how long I was not audible?
It's just short period.
Okay.
Half a minute you can say at the most.
Yeah. Oh, that's fine.
So participants, so you finished, Professor Ghosh?
Yeah, I finished.
So if participants having any doubt, you can ask 1 or 2 questions, because sir is having some other appointment immediately. You can directly ask, or you can write in the chat box. And another option is you can write to Professor Ghosh through email.
Yeah, that is definitely there. In fact, people have kind of started opening up and started writing 1 or 2 questions. I'm happy about it.
It's good. It's good that they have started asking questions.
This is always happened, because when you this course is going on in a national basis, and then people are a bit skeptical about whether should I ask questions. Yeah. But slowly people will be
opening up. They're opening up. That is a good sign. Yeah,
sure. That's a very good sign.
Okay, any question? No, I think no question. So I'll request all the participants, you please clear your doubt through email communication with Professor Ghosh. Okay.
Sure.
And if you feel so that you need some more explanation, then we can request Professor Ghosh to come in between, because we have some off days. So we can utilize one or two off days to request Professor Ghosh to clarify your doubts. Okay, that depends on how you require it. Okay, depending on your requirements, you can arrange that. I think Professor Ghosh will be happy to give us
1 or
2 more days.
Sure, no problem.
Okay, participants, then let us thank Professor Ghosh for this nice presentation of this basic parts of the NMR, how it is coming, and hope with this understanding now you can go on with the other part of the syllabus, which is with the actual application of NMR. That part will be easier for you to understand. Okay.
Okay.
Okay, and for participants, I think you have already got the information that we have some changes in the lecture schedule, because our next lecturer for the module 1 is having some other engagements, so he has to change this lecture schedule. So this is already communicated to Anu with the site. Okay. So tomorrow there is no lecture. We'll have next lecture on Monday at 5:30. This for participants. Follow our Onubidya site, so all the informations are available there. Okay, Professor Ghosh, thank you very much.
Tuesday.
Monday and Tuesday.
Monday. They are asking, student asking.
Monday, both Monday and Tuesday. Both Monday and Tuesday. We have 2 classes consecutively. Monday one at 5:30 and Tuesday one at 4 o'clock. Okay, it is already uploaded in our Onubidya site.
It is not module 1. Module 1 will start. Module 1 is...
Okay, I have already shared this today's whiteboard, correct?
Okay,
And
okay,
then
sir.
I just say all the best to all the participants, and then just let me know if you have any more clarification to make, either from my part or some other part. Correct? Okay.
Yes, so let participants independently write to you, and from our side, as it progress, we will keep in touch with you. So we need your suggestion in between. So in between, I will be disturbing you sometimes.
No problem. No problem. Okay, sure. Thank you.
Thank you, sir. Thank you very much.
Yeah. Bye-bye.
Thank you. Hello, participants. We have sent an email also to all the participants. I hope you all got it, that there is a change in the schedule for module 1 only at present. Okay. The other parts remain same as on now. So please take the note. We have lectures on Monday and then Tuesday. Then there will be some gap in between, almost 1 week gap. Then next week we'll start again. Okay, please follow the link. Latest change is already right here. See Onubidya. See Onubidya, timetable in Onubidya. See timetable in available in Onubidya. Okay. Yeah.
Okay.
So any doubt, you can just write to us. You have our email ID, so you can write to us. We'll clarify the things. Okay, thank you very much, and all the best for the next module. We'll be starting next month.